We spent a little time talking about polynomials, studying polynomials. Now we're going to study rational functions. Now, a rational function is where you have a ratio of polynomials. So we have up here p of x and q of x, where p of x and q of x are both polynomials. And what we're going to be concerned with specific properties of these rational functions that we encounter. In particular, we want to be able to determine their intercepts, the x-intercepts and the y-intercept. In addition, we want to find these things called the asymptotes. And with asymptotes, we're going to look at vertical asymptotes, horizontal asymptotes, and slant asymptotes. So let's start. First of all, vertical asymptotes. And we'll look at, to illustrate what a vertical asymptote is, I'll just look at a very basic rational function, 1 over x. And notice that the domain is any x, but x can't be 0. So in other words, x equals 0 is excluded from the domain. X equals 0 will make that denominator 0, which would make the function 1 over x undefined. But let's see what happens really close to x equals 0. So I've got a table here. Notice I've got x and I've got 1 over x. And I'm looking at different values for x, 1, 1/10, 1 100th, and so forth. And I'm plugging these values into 1 over x. In other words, notice how the x's are getting increasingly close to 0. And let's see how the function behaves when that happens. When I put in a 1 for x, I get 1 over 1, which is 1. When I plug in a 0.1 for x, I get 1 over 1/10, which is just 10, and so forth. You see how this is going. 1 over 0.01 is 100. 1 over 0.001 is 1,000. You can see how it goes. But notice, as I get closer and closer to 0 for the x's, the function gets larger and larger and larger. And I could have kept going here, I just stopped. But what happens is we get a graph that looks like this. Now notice that this graph is getting steep right here. Notice, as x gets closer and closer to 0 here, the function just starts blowing up, right? Now we could have went from the other direction, and notice as x gets closer and closer to 0 this way, the function blows up in the opposite direction. But what we note here is that as we get closer and closer to 0, the function goes off to infinity on one case and negative infinity on the other. Now let's look at this one here. Let's suppose that we've got 1 over x minus 1. The way we find the vertical asymptote is we set the denominator equal to 0. In other words, we want to find out what is the value for x that will make this denominator 0. So I take the x minus 1 equals 0 and I find that x equals 1. That is the vertical asymptote. And you can see what the graph looks like. Here's the vertical asymptote right here. And notice as x gets closer and closer to 1 from this direction, you go off to infinity, or the function goes off to infinity. As x gets closer and closer to 1 here, the graph goes off to negative infinity. So from the right, it approaches 1, the function goes to infinity. On the left, as x approaches 1, the function goes to negative infinity. Now let's look at another one. Here we've got x over 2x plus 1. To find the vertical asymptote, we're going to set the denominator equal to 0. In this case, I find it to be x equals negative 1/2. So what we see here is we've got a vertical asymptote. We find that by setting the denominator equal to 0, and here's what the graph looks like. Okay. Notice, as x approaches negative 1/2 from the left, the function goes to infinity. As x approaches negative 1/2 from the right, the function goes to negative infinity. Now, the ones we've looked at, we've either have on the one side, we're going to positive infinity, on the other side, negative infinity. It doesn't have to be that way. They could both be going to positive infinity or both be going to negative infinity. But what the vertical asymptote is as x gets closer and closer to that value that will make the denominator 0, the function goes to positive or negative infinity, as you can see here. Okay. Now, let's look at this one. Here we've got 1 over x squared plus minus 1. So just like always, I take the x squared minus 1, set it equal to 0, and solve it. And I get, this time, x equals plus or minus 1. So here is a case where we have two vertical asymptotes. And what that would look like is this. Notice. And we're not really concerning ourselves right now with how to sketch these graphs. These asymptotes kind of give us a little bit of a structure to help us to see, well, how is the function going to behave. And in this case, we know that the function goes to infinity or negative infinity at 1 and also at negative 1. So see, here's 1. The function's going off to infinity. Negative infinity on this side. Over here at negative 1, it goes negative infinity on the right. I mean on the, well, my right. You're right. And as we approach from the left, it goes off to positive infinity. See? But the thing is, the graph goes off to one positive or negative infinity as x gets closer and closer to those asymptotes. As x gets closer and closer to the point at which the asymptote passes on the x-axis. Now, let's think about horizontal asymptotes. Now, horizontal asymptotes, we'll explore this the same way. We'll go back to this f of x equals 1 over x. And I'll make a table. And this time, notice what I'm doing. I'm not having x get closer and closer to 0. I'm having x get larger and larger and larger. 1, 10, 100, 1,000. In other words, the horizontal asymptote helps describe the behavior of the function as x is going to either positive or negative infinity. That's what the horizontal asymptote does. The vertical asymptote helps describe the function as x gets closer and closer to some number. But now we're having x going off to infinity. And let's see what happens here. 1 over 1, that's 1. 1 over 10, that's 0.1. 1 over 100, that's 0.01. 1 over 1,000, see, I'm taking this 1,000 and putting it in for x. I get 0.001, and so forth. But what you see here is that as x gets larger and larger and larger, the 1 over x is getting closer and closer to 0. So the graph would, and so we look at the graph again, and you can see as x goes to infinity, the function is getting closer and closer to 0. So that's the horizontal asymptote. Now, how do we find the horizontal asymptotes? That's the question. Well, we're going to look at three cases. Case 1 is a situation like this. And now what I'm doing is I'm just writing a very simple one. ax to the n plus b, and this could be a lot more complicated. This could be ax to the n plus bx to the n minus 1 plus c x to the n minus 2, and so forth. I'm just writing a very simple polynomial here up top, a very simple one on the bottom, and I'm just using n. Now you see here that the degree of the top and the degree on the bottom are the same. So this is case 1, when the degree of the top and the degree on the bottom are the same. How do you find the horizontal asymptote in that situation? Well, let's take a minute and just explore this. Let me multiply the top and the bottom by 1 over x to the n. Just a little trick to help us to see what's happening as this x goes to infinity. And I took the largest power here, and I just divide it by x to the n on the top and the bottom. Now, it's fine to do that because this is like multiplying by 1, right? 1 over x to the n divided by 1 over x to the n. It's just like I'm multiplying by 1. Now, if I distribute through there, and multiply each term on top by 1 over x to the n, this is what I get. Now, notice this cancels, x to the n over x to the n, x to the n over x to the n here. Okay, so those are taken out, and here's what we have left. Now, look, as x goes to infinity, look what you have here. You have a constant over this thing that's growing larger and larger and larger right here. Well, when you have a constant over something that's getting increasingly large, that's just going to be 0. Now we have 0 here and here. So here's what we find. As x goes to infinity, this term and this term go to 0. And all we're left with is a over c. The ratio of the leading coefficients. So here's case 1. If you have the degree of the top and the degree of the bottom are the same, the horizontal asymptote is the ratio of the leading coefficients. In this case, it's a over c. Now let's look at case 2. Let's suppose the degree on the bottom is bigger. Now we're assuming here that k is some positive number, okay? And so we have ax to the n up top and cx to the n plus k on the bottom. So the bottom has a bigger degree. And of course, we're saying k is some positive integer, okay, or some positive natural number, let's say. That's a better way to say it. But the degree on the bottom is bigger than the degree of the top. Okay, so let's see what the horizontal asymptote might be. In other words, how does this function behave as x goes to infinity? Well, I'm going to multiply the top and the bottom by 1 over x to the n plus k. So that's the trick I'm going to use here. If I distribute 1 over x to the n plus k, I get this situation. Now notice some things will cancel, and I'm left with this. Now, dig this. As x goes to infinity, this first term goes to 0, the second term goes to 0, and then the last term down here goes to 0. And all you're left with is 0 over c. Well, that's 0. So as x goes to infinity, f of x goes to 0. So we say here, in this case, where the degree on the bottom is bigger than the degree of top, the x-axis is the horizontal asymptote. Or, y equals 0. Now, case 3. So let's look at this case 3, and it's the case where the degree on the top is bigger than that of the bottom. So if you look at this, and let's do this trick. Let's multiply the top and the bottom by 1 over x to the n to kind of illustrate what happens as x goes to infinity. And if we do that, here's what we get. X to the n under the first term, the second term, same thing we've been doing. But notice what happens. These x to the n's cancel down here. And over here, you've got this term, and this right here. Now, notice that these two terms go to 0. And what we're left with is ax to the k up top and just a constant on the bottom. Well, if you've got this x growing up top and just a constant on the bottom, what you have is a situation that as x goes to infinity, f of x goes to either positive or negative infinity, depending on what the signs are. So there is no horizontal asymptote in this case. Now, let's look at an example where we kind of tie everything together. Let's suppose we want to get a basic sketch of this. We want to get an idea about how this graph is behaving. Well, we first of all find the y-intercept. Now this is important. Always to find the y-intercept, you replace the x with 0. And when we do that, what we get is 6. So we have that this graph crosses the y-axis at 0, 6. Now, we find the x-intercept. We set the top equal to 0. Now, actually, to find the x-intercept, you set the whole function equal to 0. But look, the first thing we would do is multiply by x plus 1. And if we multiplied by x plus 1, we would just get 2x plus 6 equals 0. We'd have this. Now, you can see that whatever makes 2x plus 6 0, whatever makes the top 0, makes the whole thing 0. So when you're solving a problem like this, when you're looking for the x-intercepts, just set the top equal to 0. And we get x equals negative 3. Then we talk about the vertical asymptote. The vertical asymptote we find by setting the bottom equal to 0 and solving. Get x equals -1. Horizontal asymptote, well, this is definitely case 1 because notice the degree on top, degree on the bottom are the same. So the horizontal asymptote is the ratio of the leading coefficients, 2/1. And here's what that graph would look like. Notice we've got the y-intercept here at 6. We've got the x-intercept here at -3. Vertical asymptote, horizontal asymptote, and there you have it.